Welcome to this second lecture of array antenna. We were seeing n element array and we have found out what is the total field due to all the radiators. And if you notice in the last expression, we have substituted actually for each one this 4 pi r, that actually it is different for different one, for R1, R2 etc. it should have been, but since this is the amplitude part, we have put for everyone, we have put the far field formula that all Ri's are same, that is why here Ri, but here we have not done that, here we have put the exact condition. So, now we can say that if you look at it, this whole thing is a element pattern. So, can I claim that this is element pattern, because you see this is the same as this. So, element pattern and this is the array pattern. So, this is the principle of pattern multiplication. So, in general also it is valid, it is not that only for 2 or only for a symmetric thing. Any n element array you can always break that this thing, and generally this small one we called small f theta and this one array factor, we generally write it as f theta phi, because here also between these angles there are this theta phi is present. So, now study of array antenna is basically this study of this array factor. So, I can write the array factor capital theta phi, that is nothing but I is equal to 1 to n C I e to the power j alpha I e to the power j k naught A r dot r I. Now, radiation pattern will be square of the magnitude square of this, and directivity is I write here that directivity of the whole array antenna can be written as f theta phi square minus . Okay. But finding directivity, we will see that in case of array factor there will be a directivity, and this factor already we know how to calculate directivity of elemental ones. So, the total directivity will be this thing, but always finding the directivity from this thing array factor is not so easy. We will see some simple cases where we can have approximately find these, but the end result is obviously directivity increases much because of array, that is why arrays are used to give directivity nature in particular directions, and typically 10-15 dB increase in the directivity function can be done with a very simple practical arrays. Now, here I need to point out one thing, that in this all these cases we have assumed that this f theta phi for all elements are same. If we look at this view graph, that all these antennas they are identical antennas. So, their f theta phi is same. Now, pattern multiplication assumes that everyone is having these, but realistically in practical cases this is not true, because if you have an array antenna, now since they are very closely spaced together, actually we will prove later that array antennas need to have the spacing need to be less than one wavelength now for all array antennas. So, there will be strong mutual coupling between them. So, if I have a large array, so the central elements and the far away elements or the extreme edges element, their pattern is not same because of mutual coupling. Now, that is neglected in pattern multiplication. So, if in an actual evaluation that mutual coupling, if it is not taken into account, then the whole calculations goes array. So, pattern multiplication is a simplified one, but at your level, undergraduate level or graduate level, that is okay, but in the research level or actual evaluation, there are ways to factor into that mutual coupling factor. Now, hereafter we will study only the array factor, and we will start with the first type of array is uniform linear array. Now, uniform, there are two types of array, uniform or non-uniform array. Now, uniform does not mean that or non-uniform does not mean that the array elements are non-uniform, no. Always in array theory all the elements are uniform, but uniform linear array means the spacing between all the elements are same. So, spacing is uniform, this is the meaning of uniform array. Linear means the all array elements are placed along a line. So, this you see that I can say here again you can see that this is dipole, but it could have been anything. Here without loss of generality we have assumed dipoles. This could have been monopoles, this could have been horn antennas, this could have been open ended waveguide antennas, etc., etc. Now, you see that the elements are placed along x axis, a line, and there are n plus 1 such elements, because first one we are naming 0, 1, 2, etc., I, then it goes to capital N. So, this observation point is here P, again these are distance. So, this psi is a solid angle, this is a solid angle. So, the observation point or radius vector of the observation point makes an angle psi with the array axis. This is the standard terminology that we will follow. Okay. So, array axis is x, and from that at an angle psi we have the observation point. Here is the unit vector, and here we say that each antenna is excited with same constant amplitude, and since we have assumed dipole, now we can say that amplitude excitation is current I naught, but with a progressive phase shift. The phase shift is alpha d, this is called progressive phase shift. So, I can say that the phase shift of the nth element, small nth element, that will be n alpha d. So, I can write what will be the array factor I naught n is equal to 0 to capital N e to the power j n alpha d plus j k naught n d cos phi. Why I am writing this? Because you see my previous expression was this. This is okay. K naught AR dot RI. So, what is the value of AR dot RI? In this case, AR is equal to AX and RI, or you can say RN will be N D AX. So, AR dot RN is equal to ND cos psi, and that is equal to ND. Can I write sin theta cos phi? Okay. So, I can put this, and what is this? This is a geometric series. So, in a geometric series, if I have, I can say that it is the, what is that, geometric ratio. No? Suppose I have sigma. So, what is the value? 1 minus omega, since I have n minus 1. Okay. So, similarly here I can write f theta phi is equal to I 0 1 minus e to the power j n plus 1 alpha plus k naught cos phi d by 1 minus e to the power j alpha plus k naught cos phi d. So, again the trick is, you take half of this out. So, e to the power, or I naught will be there, and take a common e to the power j n plus 1 by 2 alpha plus k naught cos psi d, and here you take e to the power j alpha plus e to the power j alpha plus k naught cos psi d by 2. Then you can write it as e to the power minus j n plus 1 by 2 alpha plus k naught cos psi d minus e to the power plus j n plus 1 by 2 alpha plus k naught cos psi d divided by e to the power minus j alpha plus k naught cos psi d minus e to the power plus j alpha plus k naught cos psi d. That is all, pretty simple. So, this becomes I naught e to the power j n by 2 alpha plus k naught cos psi d sine of n plus 1 by 2 alpha plus k naught cos psi d by sine of alpha plus k naught cos So, this is array factor and this is also field expression. So, array field pattern will be, I can easily write what is f is I naught, this will go for amplitude and this is nothing but sin n plus 1 by 2 Now, do not get frightened by looking at big expressions. These are simple expressions, maybe looking big, we will just take steps to simplify that. So, that becomes manageable. What are those steps? Very important steps, that we will just assume two things, we will introduce two new variables. One is u is equal to k naught d cos phi and u naught is equal to alpha d. So, the same f, that theta phi is now in terms of u. So, it is a function of u now and this becomes I naught sin So, if we plot this function in the u plane, that means x axis is u and this magnitude is this, it becomes something like this. So, you see that there is a maximum value, a main lobe, then there are side lobes progressively decreasing, and since this is magnitude, all are positive. So, this is something like sinc function, but only difference is that this is a periodic function, sinc is not a periodic function. So, this is, you can say, behaves much like our normal sinc function, which is sin u by u, but here this is sin n plus 1 by 2 u by sin u. So, this is a different function, this is the heart of array antenna study, this is called array function. Now, here you will see that we have plotted versus u, but we will see that this all values of u are not physical values, because we will see that. And the important thing to note from here is that the peak comes at a point where u is equal to minus u naught. So, the peak is not at u is equal to 0, peak is at u is equal to minus u naught. If you make u naught to be 0, then the peak comes at u is equal to 0. Now, what is u naught? U naught is dependent on the progressive phase shift. So, if I do not give a progressive phase shift, which we have seen, we do it in broadside cases, then the main beam will come at this point, but otherwise it is at minus u naught. Okay. And we can find out what is the, I will explain later why this visible space and all these things are called, because those are important things. And you may note that in array things we have a beam width definition slightly different from the normal antennas beam width. In antennas beam width we have a generally 3 dB or something beam width. Here we are taking the beam width definition to be null to null. That is the only difference. That time also we have said that null to null can be taken. Generally in an array antenna we take null to null beam width. Okay. And what are the main lobes? So, whenever we get u plus u naught by 2 is equal to m pi, you see u plus u naught by 2, if it becomes m pi, then I can get a main lobe, because this actually that time this is the singular case, that 0 by 0 case, and that is much greater than any of the actual maximum of this point. So, u plus u by 0 m pi, where m is any integer. So, now you can find what is the first main lobe will occur at u plus u 0 by 2. So, I can say first main lobe is, that means u is equal to minus u 0, and what is the value of that? F major lobe maxima value. Here we will have to apply the L hospital rule, we will have to differentiate. So, you do that and you will find that it will be I naught n plus 1 by 1, that is I naught n plus 1. So, basically in the main lobe maxima, all the radiated fields from elemental antennas are added in phase. So, at that point all are added in phase. Now, let us come to the side lobes. When side lobes will occur, what is the condition of side lobe to occur? The numerator sine function should be maximum or 1 and denominator is not 1, then only we will get a side lobe. So, put that condition, that means what is a side lobe maxima condition, that is n plus 1 u plus u 0 by 2 is equal to plus minus 2m plus 1 pi by 2, and I will have to exclude the main lobe condition, m is equal to. So, now is not it? So, from this you can see that the amplitude of the side lobe maximum will vary, as also can be seen in the graph. You see that amplitude is varies, we can find the nearest one. Nearest one will be, I can write f minor lobe first maxima, that will occur at I naught, the first m is not 0. So, the first value it can take is 3, when m is 1. So, sin 3 pi by 2 by sin 3 pi by 2 n plus 1. please note that m is equal to 0, this thing becomes what? Plus minus pi by 2, and that does not give a minima because this also becomes very high. So, this is I naught 1 by sine 3 pi 2 n plus 1. For large n, how large? Typically, if n is greater than equal to 8, we can say that sine 3 pi 2 n plus 1, that is the argument of sine is very small. So, it can be approximated by the angle itself. So, we can put that this is approximately I naught 1 by 3 pi by 2 n plus 1. So, it becomes okay. So, that means please look at the diagram that this is this value and we know this value. So, let us compare. F first minor lobe maxima by F major lobe maxima. I naught n plus 1 by I naught n plus 1 2 by 3 pi. So, that becomes 2 by no, this should go up 2 by 3 pi, this should be down, is equal to 2 by 3 pi, and that value is 0.21 and that is minus 13.5 dB. So, this is a general, this is a truth that any uniform linear array, the first side lobe is only minus 13.5 dB down the main lobe. This is a serious problem in any practical work. By hook or by crook, you cannot avoid this. So, uniform linear arrays need to be improved, because in practical cases at least minus 30 dB the side lobe should be down. It is better if it is more, but at least minus 30 dB down is necessary for any radar or other type of applications. So, uniform linear array cannot foot that bill, and that is why people have non-uniform arrays and other things. But this you should always remember that this is a law of nature, you cannot bet the, and this is independent of the number of elements in the linear array. So, provided n is at least 8, which is typical. So, if n is greater than 8, then even if you go on pumping more and more arrays, you cannot put the side lobe down. That will see that if you go on increasing the length of the array, your main beam will be much narrower, that means your beam width will be decreasing, main lobe will be a thing, but the side lobe you cannot put it down more. Actually, okay, and where are the nulls? Nulls are easy to find, because if you see the actual function, so whenever this will give a this whole thing is pi sort of thing, or multiple of pi, even multiple of pi, this won't be even multiple of pi. So, never 0 by 0 case will come. So, based on that, so what are nulls? Nulls of the pattern are n plus 1, u plus u0 by 2 is plus minus k pi, where k is odd even numbers. So, main lobe nulls occurs at n plus 1 u plus u0 by 2 is equal to plus minus pi. Okay. As a function of u, the array pattern repeats. You can see the array pattern. So, array pattern repeats every 2 pi units along the u axis. If you put it here, u plus 2 pi, you will see that the whole thing is repeating. And we now note that what is u? U we have introduced to be this. Now, cos psi, that can take only, cos psi is nothing but sin theta cos phi. So, that can take value plus 1 or minus 1 at the most. That means, the range of u corresponding to physical space, because this psi or this theta phi real means this is real, real means this is physical. So, visible region, can I say that that will extend from minus k naught u plus k naught u, because cos phi is from minus 1 to plus 1. Cos phi is varying this. So, physical space is this. That means, u is having a physical value as long as this. The range of u corresponding to physical space, that is called visible region. But actually, after every 2 pi we can go on, and actually there is techniques by which you can change various antennas, array antennas performance if you go into the invisible domain. Actually, that is the way by which the antennas, reactive impedance array antennas can be changed. That is an interesting story. Fortunately, after my BTech, I was introduced to that. That was my first professional assignment after passing out, and we have a publication from there. So, okay, but this visible region, so you can see that is why here we are making the visible region is visible space is k0d to minus k0d in this figure, which is this value. So, also you can in practice we require only one main lobe to occur in physical space. If more than one comes, that means in this space, that means from here to here, instead of this main beam, another beam, that means you see this is another beam's peak. Now, if by some array design this can be changed and come to this space, then there will be more than one main beam in the visible space. So, that time this is called grating lobe. So, if more than one main lobe comes into the visible space, then they are called grating lobe. To avoid grating lobe, we choose the spacing D small enough, so that the region plus minus 2 pi d by that plus minus this cannot d by 2 means minus 2 pi by lambda naught d 2 pi by lambda naught d. So, the total region is 2 pi d lambda naught. So, that region plus minus d by lambda naught on either side of u is equal to on either side of u naught does not include another main lobe. So, that is done by the spacing. So, that means if you make spacing large, you can avoid you can invite grating lobes into the visible zone. So, we will see that what are the requirements on D in the next lecture, and actually there are two special cases of this uniform linear array. I have already mentioned, we have shown the photograph for two element array. One will be called broadside array, where the radiation or major lobes peaks perpendicular to the axis of the antenna, and another is end fire array, where the maximum radiation or main lobe is along the axis. So, we will see them one by one, broadside array and long side end fire array. The terms come from radar days. Those times it was pointed with the that what is that armory, artillery. So, broadside, end fire, all these, that before firing they used to align it, from that the terms came. Okay, thank you.